Welcome to The Explainer. I am so thrilled to have you here today. Look, if you've ever worked with modern software deployment, you've undoubtedly crossed paths with containers, right? I mean, they're basically the absolute bedrock of today's cloud computing landscape. But there is a massive misconception out there about how they actually work. So today, we're going to set the record straight and uncover the true underlying mechanics behind Linux container architecture. We are going to literally peel back the layers of abstraction and see exactly what is happening under the hood.
To start us off, let me pose a scenario that probably sounds pretty familiar. Why doesn't one buggy container crash the whole server? Imagine you've got a server running, say, a dozen different containers. Suddenly, a nasty little bug in the code of just one of those containers causes its CPU usage to violently spike to 100%. Now, in a normal environment, that server would just choke, taking everything else down with it. Yet, incredibly, the other containers on that exact same host machine just keep humming along perfectly fine, completely unfazed. How is that level of isolation actually achieved?
Okay, let's dive into this. And right off the bat, we're going to bust one of the biggest myths in the tech world. So many developers will confidently tell you that Docker is just a lightweight virtual machine. But actually, scratch that. It's a massive misunderstanding. A traditional virtual machine is heavy, it's bloated, because it truly virtualizes an entire hardware stack and runs a complete, heavy guest operating system right on top of a hypervisor. A Docker container, on the other hand, completely different beast. Fundamentally, it's just a normal, single process running directly on the host operating system. It's not a machine at all, it's just a highly isolated process.
So, now that we've busted that myth, here's our roadmap for today. 1. Docker is not a VM. 2. Namespace and cgroup explained. 3. The magic of cgroup. 4. Docker in action. And 5. Evolution to cgroup v2.
Let's jump right into Section 2, Namespace and cgroup explained.
Let's look at the first pillar making this whole illusion work, namespace. If a container is really just a normal process on the host, how on earth do we make it believe it has the entire machine to itself? Well, the Linux kernel pulls this off by putting a sort of magic blindfold on the process. That blindfold is the namespace. It provides strict visual isolation. Once a process is dropped inside a namespace, the kernel hides absolutely everything else from it. The process looks around and nothing. It can't see other files, it can't see the wider network, and it can't see any other process IDs. It looks in the mirror and genuinely thinks it's PID1, the ruler of its own isolated little world, even though, in reality, it's just a heavily restricted process on the host. But as you can probably guess, visual isolation is only half the battle here. If our blindfolded process decides to go totally rogue and chew up 100% of the CPU or eat all the RAM, the whole server is still going to suffer. That is exactly where our second pillar comes in, cgroup, which stands for control groups. Think of cgroup as a strict financial minister, or maybe picture it like a giant robotic arm descending from the sky to firmly hold the process down. While namespace provides the blindfold, cgroup slaps on the physical handcuffs. It strictly enforces resource limitations and auditing, ensuring our isolated process gets a highly specific, very limited ration of the host's actual physical resources.
To summarize this division of labor, because it's absolutely crucial, namespace is entirely about visual isolation. It strictly dictates what a container can see. On the flip side, cgroup is entirely about resource limitation. It dictates what a container can use. Without namespace, the process knows it's sharing the system. Without cgroup, the process can greedily consume the entire system. Put them together, and boom, you've successfully created the container illusion.
All right, moving on to Section 3, the magic of cgroup.
The way Linux actually manages cgroups is, honestly, absolutely brilliant, because it treats the whole thing entirely as a file system. Specifically, cgroup relies on a virtual file system, or VFS, which is normally mounted right at /sys/fs/cgroup. Within this directory structure, you're going to find what are called subsystems. We're talking directories for CPU, memory, Black I/O for your disk read and write speeds, and PIDs. You can essentially think of each of these subsystem directories as its own individual resource manager, holding specific jurisdiction over a particular type of hardware resource.
Now, what's really interesting about this exact number here, 524,288,000, is how remarkably simple the underlying mechanism is, because cgroup is completely file-based. Applying a restriction is almost laughably easy. If you want to limit a container's memory to exactly 500 megabytes, you don't have to wrestle with some complex API. The Linux kernel simply requires you to create a new folder inside that memory subsystem directory and write this exact byte value, which equals 500 megs, into a specific text file named memory.limit_in_bytes. That's literally it. The kernel reads that text file, and the ironclad limit is instantly enforced. No way around it.
Let's see how this plays out in the real world in Section 4, Docker in action.
Consider a command you might type out every single day. Docker run -d --name myweb -m 500m ngx. In plain English, we're just telling Docker to run an ngx web server in the background, and we're strictly capping its memory usage at 500 megabytes. It looks like a simple, everyday command, right? Well, let's reveal the actual dirty work Docker is doing behind the scenes the second you hit enter.
Docker is basically acting as an incredibly fast foreman for us, interacting directly with the Linux virtual file system on our behalf. Step 1. Docker goes into /sys/fs/cgroup/memory/docker and creates a brand new folder named with this specific container's unique ID. Step 2. It takes our 500 megabyte request, converts it into bytes, and writes that exact number into the memory limit configuration file inside that new folder. Step 3. Once the Nginx process actually spins up, Docker grabs its process ID, its PID, and drops that number right into a file called cgroup.procs. The exact moment that PID hits the file, the kernel formally links the Nginx process to the 500 megabyte limit. The handcuffs are securely on.
But of course, this naturally raises a pretty suspenseful question. What happens if the container just disobeys? Let's say our Nginx container gets hit with a massive, unexpected spike in traffic, ignores the rules, and desperately attempts to use 501 megabytes of RAM. Does it crash the server? Does it just fail silently?
Enter the ultimate villain of the Linux kernel, the OM killer, or out-of-memory killer. The very microsecond that process attempts to cross the 500 megabyte threshold written in that text file, the group memory manager trips an alert to the kernel. The kernel then unleashes the OM killer, which ruthlessly and instantly executes the non-compliant process. If you have ever stared at your Docker logs and seen a container mysteriously die with the infamous exit code 137, well, now you know. That code is literally the chalk outline left behind by the OM killer after a container tried to breach its group limit. Finally, let's wrap up with Section 5, Evolution to Group v2.
So there are actually two major eras of this technology. cgroup v1, the older version, relied on multiple, completely independent trees. CPU limits were living in one tree, memory limits in a totally separate one, and disk I/O in yet another. Because they all operated completely independently, coordinating them was incredibly difficult, which led to some really frustrating bugs when processes spanned across multiple resources. Well, cgroup v2 completely solves this architectural flaw. It ditches the independent branches entirely and enforces a single unified hierarchy. Everything is managed under one unified tree now, allowing for perfect coordination between CPU, memory, and I/O. And for sure, modern Linux distributions, along with recent versions of Docker and Kubernetes, have completely embraced this v2 architecture.
And this brilliantly illustrates the whole picture. When you finally pull back the curtain on containerization, you find these three distinct actors working together in this grand synthesis. Namespace is your magic blindfold. It provides the visual isolation. cgroup is your strict financial minister. It enforces those hard physical limitations. And Docker? Docker isn't a virtual machine at all. Docker is simply the highly efficient foreman. It's just a tool that wraps up the manual, tedious process of creating folders and writing to kernel text files, fully automating these incredibly powerful native Linux features.
Which brings us to our final, somewhat provocative thought for this explainer. Now that you know the deep magic of Docker is essentially just text files hiding in a specific directory, the question is, have you checked the cgroup files on your own server yet? I highly challenge you, the next time you SSH into a Linux machine, just navigate over to /sys/fs/cgroup. Poke around a bit. Look at the actual text files restricting your active containers. Seeing it with your own eyes entirely changes the way you understand cloud infrastructure. Thank you so much for hanging out and diving into this with me today. As always, keep learning and keep exploring.